on the last lecture, we introduced the concept of isomorphism. And in the very end of the last lecture, we have proven the following lemma, that essentially an isomorphism maps a zero vector to a zero vector. So essentially, so proof was like that. So let me remind you. If this is isomorphism, so let us choose some V which belongs to the original vector space V. Then if I apply my isomorphism to the zero vector in the vector space V, I can write it. So we have proven that in any vector space, if you multiply any vector by zero scalar, right? So you will get a zero vector. So this is nothing else but that, right? But then using preservation of structure of the isomorphism, you have this, but this by definition of isomorphism belongs to the, it's some vector from the vector space W, right? One-to-one and onto. So what is important, onto, which means that all vectors from W are results of application of our map to some vector in V. So, but then, because any vector multiplied by the zero scalar is a zero vector, we are getting that this will be all zero vector in the W space. So pay attention here. I haven't used specifically what are these vector spaces, what particular map I'm using. The only fact which I used is that this is isomorphism. So, and it means that first of all, it's onto, and also it preserves structure. So this particular equality is a result of preservation of structure, right? Okay, now let me formulate another lemma, which we will use later. So for any map, pay attention. Here I'm saying any map, right? So F V onto W between vector spaces. So which means any map mapping vector space V onto vector space W. These statements are equivalent. Statement 1, F preserves structure. So here V1, V2 belong to the vector space V, and C is a scalar. Really, it's not necessarily real, but as I said in the very beginning of this course, we will limit ourselves with real scalars for the course. Really, of course, it can be complex. F preserves linear combination of two vectors. What does it mean? It means that this I already have shown that from here, so that these and these are equivalent. So either these two statements, or this one statement. So this I already have shown before. 3 F preserves linear combination of any finite number of vectors. Okay, so I told you already that when we say that these statements are equivalent, so naive way of proving it is to show that from 1 follows 2 and 3, from 2 follows 1 and 3, and from 3 follows 1 and 2, right? So, but then we need to do 6 proofs, right? 1, 2, 3, 4, 5, 6, right? So, and the more, let's say, the smarter way to do this is to show that, for example, from 1 follows 2, from 2 follows 3, and from 3 follows 1. Or in whatever other way. So, for example, it's easy to show that from 3 follows 2, from 2 follows 1, and then all we need is to show that from 1 follows 3, right? Is it clear or not? So, okay, proof. From 3 to 2. First. Okay, from 3 to 2, it's an obvious case. So when n is equal to 2, right? Right? So if I limit n by 2, so I'm getting exactly statement 2, right? Is it clear or not? Thank you. So now, from 2 to 1, could you tell me, so what I need to do in order to prove that from 2 follows 1? So if 2 is true, how to show that these two statements will also be true?
Would you just say that C equals 1?
Okay, right. So if I consider this, right, C1 equals 1 and C2 equals 1, right, then statement 2 becomes nothing else but that, right? Is it clear or not?
It's clear.
Okay, so now let me consider C1 equals to C and C2 equals to 0. Then have a look. C1 equals to C2 equals to 0. So eliminates this and these parts, right? And C1 equal to C gives me exactly this condition, right? Okay, now I need to show that from 1 follows 3. Okay, we will do this by induction. So first of all, n equal to 1. So results in the following: f c1. The case n equal to 1 follows from here immediately, from this, right? So works, right? For n equal to 1. Is it clear or not? So have a look. I need to show that from 1 follows 3. So I'm saying that let us first check that it works for just in usually in induction proof, we consider some base case, right? So n equal to 1. So then none of these terms are present. So we are getting just f of C1, and I can use this statement, right, to show that it works for n equal to 1. Is it clear or not?
Yes, it's clear.
Okay. Now, I suppose suppose it works for k. N equal to k. So what does it mean? It means that f c1 v1 plus c2 v2 plus and so on plus ck vk equals to c1 f v1 c2 f v2 plus and so on plus ck f vk. Right? So we suppose that it works, and now all we need to do, we need to prove for that it also will work for n equal to k plus 1. Okay, let us consider it. So let me denote. Oops. Let me denote this as v, right? Then I'm getting f v plus ck plus 1, vk plus 1, right? Okay, this is just some vector which I can call w, right? So I'm getting f v plus w. But then, so we are going from 1 to 3, right? So I can use this condition, the first condition, right? And I'm getting that this is equal to f v plus f w, or it's equal to f, what is v, c1 v1 plus and so on, plus ck vk. And w is nothing else but so, because we said that suppose it works for k, right? So then these can be represented as these, right? But then, because we suppose that this works, so we're starting from 1, right? So I can use second condition here, and it would give me on this, I mean, and it would give me ck plus 1 f vk plus 1, right? But then I got exactly that it works for n equal to k plus 1, right? Is it clear or not? So you see, I supposed that it works for n equal to k, where k is arbitrary, right? So just some given integer, right? And then I have shown that if it works for k, then using the statement 1, it has to work also for n equal to k plus 1. So it means that now, starting from k equal to 1, I know that it will work for k plus 1, which means for 2, right? From 2, I know that it works for 3. For 3, n equal to 3, I know that it works for 4, and I can go like that infinitely for any number n. Is it clear or not?
It's clear why it like proves it. I'm just like a little confused with the steps from n equals k to n, well, pretty much just the steps with n equals k plus 1.
So, okay, idea is the following. So I need to prove that this formula, right, this one, works for n equal to k plus 1, right? So essentially, this is it, right? So this is exactly the statement which I have written for n equal to k plus 1, right? Now, I said that, okay, let me call this, let me denote it by letter v, because linear combination of vectors is, again, a vector from the same vector space, right? So here it is v, this part, right? And here is this part. And I said that, okay, let me call this part as vector w. So is it clear up to here?
Yeah.
Okay. Because why I can do this, because I know that there is a closure with respect to multiplication by the scalar, right? So I take any vector from the vector space, multiplied by the scalar, and I has to get also vector from the vector space. So now I have this, right? But because I'm going, okay, let me erase. So we went from 3 to 2, from 2 to 1, and now I'm going from 1 to 3, right? So I'm trying to prove that if 1 is true, then 3 is also true. So if 1 is true, so then this works, right? So, but this is exactly this statement, right? So that from here, I will get this. Is it clear or not, this step?
Yeah, but for me, I guess it's just a little confusing. Like, why did you have to like name it V and W? Why can you just say, okay, this is we see in the previous like establishment. So like
No.
yeah,
I will explain. You see, so the statement is the following. So that all these three statements are equivalent, right? This is the statement of the theorem. So you see, I need, so from the part 3, I have shown how to get part 2, right? So you just put in n equal to 2, and this is exactly part 2, right? Now, you see, I cannot use the 3 because this is the logic. So I'm going from 3 to 2, but now I need to go from 2 to 1. So I essentially saying that, okay, let me suppose that 2 is true, right? Now I need to show that then 1 will be true. So this is exactly what I did here when I said that the two statements in 1 are special cases of statements in 2, right? Clear?
that's clear.
Okay, and now I need to start from the statement 1 and 1 alone. You see, I cannot go back in logic. So I cannot go back in logic because if from one logical statement follows another one, it doesn't mean that necessarily from the second statement follows the first one, right? So for example, all integer numbers are real numbers, right? But not all real numbers are integer numbers. Clear?
Clear.
So I cannot go back in this chain of logic, you see? So I can go only, so I have shown this only in one direction. So now I have shown these in this direction, right? So, but these I cannot do for now. But if I will close this chain of logic, right? So I create a loop. Then along this loop, it means that I can go from any statement to any statement. Is it clear or not?
Yes, that is clear.
So, and now have a look. I need to go, so essentially these and these are easy. Now I need to go from 1 to 3. It means that I can use only these two statements, right? And from them, I need to show that 3 follows. Clear or not?
So
Yeah,
n plus 1 creates a second vector. Or k plus 1, I'm sorry.
Yes, so you see, for n equal to k, we have here exactly k, linear combination of k vectors, right? Right?
Yes.
So now, when I consider case n equal to k plus 1, I need to consider linear combination of k plus 1 vectors, right?
Yes.
So now I need to use only statement 1, which means these two conditions, right? And so-called induction hypothesis. So when I said suppose it works for n equal to k, to prove the statement, statement for n equal to k plus 1. So exactly for that, I denote this. I know that linear combination of vectors because I have closure with respect to the linear combination, right, of vectors for the vector space. So I know that V is a vector belonging to my original vector space V, right? And W is a vector, so because I have closure with respect to multiplication by the scalar, which belongs to my original vector space V. Now I get this expression. This expression already exactly this, right? Is it clear or not?
Yeah, so we don't have to continue going. We could add a vector z by x equals k plus 2 and so forth. But for our purposes, we just need two vectors to prove 1 to 3 to
No,
1 to 3.
I cannot use more than two vectors. You see, I cannot use more than two vectors because here the thing which I highlighted right now, it works only for two vectors. You see?
Yes, but I was just commenting that in 3 for the proof of 3 to 1, I think that's no 1 to 3, that if you added k plus 2.
If I need to go from 3 to 1, it's easy because I essentially for the first statement, I need just to put n equal to 2 and C1, C2 equal to 1, right? For this statement, I need to put n equal to 1 and C1 equals to C, right? But I'm going in the opposite direction. I'm going from 1 to 3. I'm starting from this statement 1. And from there, just using the statement 1, I'm trying to prove that statement 3 is also will work. Is it clear or not?
Yeah, so pulling out the C1 to CK from number 3, or from number 1, or from K plus 1.
You mean from here, right? So when I'm doing it here, when I pull out this this part, right? I mean, okay, yeah. So I used my induction hypothesis for this, and I've got this expression. Is it clear or not?
Yes, and that shows the second part of 1.
Wait a little bit. So then, for this statement, right? I used second part of 1, right? Clear?
Yes.
So once again, the blue statement, the what is highlighted with blue is nothing else but exactly my induction hypothesis that says that let's suppose it works for k. So suppose, yeah, by the way, suppose works for n equal to k. Clear now or not?
Yes.
So now I can use only my statement once, the statement from 1, and these hypotheses that it works for k. So I need to prove using that knowledge that it will work for k plus 1. This is exactly what I'm doing here. You see? So I first created this, and this is nothing else but this is nothing else but this statement, which is covered in blue here. I mean, highlighted in blue, not blue, green, sorry. So this one. Clear or not?
Yes.
So you see, I started from the induction hypothesis. Let us suppose that it works. Let us suppose that it works for k. Now, for k plus 1, I first use statement 1 to get this, right? Then, because v is nothing else but that, right? So I can use my induction hypothesis when I said that suppose it works for k, right? And now I've got that it works these, right? And for this part, I used exactly the second statement, this. So f of cv equals to cv, cf of v, just this. And now I have proven that statement 3 works also for n equal to k plus 1. So you see, I suppose that it works for k, where k is arbitrary integer, right? And I have proven that it will work for n equal to k plus 1. What does it mean? It means that now I can start from my base case, which follows immediately from the second requirement of the first statement, right? I can start from n equal to 1, and I know that, so k is equal to 1 in this case, right? So, and I know that it will work for n equal to 2. Now, I know that it's proven for n equal to 2. Now I can say that, okay, it works for k equal to 2, then it has to work for k plus 1, which is 3, right? From 3, I can go to 4, and so on to any finite number n. Clear or not?
Yeah.
So any questions with this induction proof?
Will this be a proof that we use to prove our work in an exam or quiz or homework?
So
for example?
you see, I will never ask you to do induction proof in the main part of the exam, but of course it can appear in if there will be at all extra points or some extra points problem or something like that. So because there I can ask you essentially anything what we studied. So but I believe some of the homework problems will require that. Some of the I mean some of the harder homework problems will require that. Okay, is it clear or not what? So that I have proven that these three statements are equivalent. Any questions here? Okay. So now let us continue working with isomorphisms. The inverse of an isomorphism is also an isomorphism. So proof. Suppose that we have isomorphism from V to vector space V to vector space W. In other words, suppose that V is isomorphic to W. So because we have one-to-one correspondence, right? So for every, and we have onto, right? So that for any W belonging to the vector space W, there exists V belonging to V such that f of V equals to W, right? So because we have onto, it means this, and because we have one-to-one, it means that this V is unique. So it means that I can introduce inverse function from W to V. Okay, now this is also a correspondence. So which means one-to-one and onto. So now all we need to do, we need to prove that inverse function also preserves structure. Let us consider any W1, W2 belonging to the vector space W. So because F is one-to-one and onto, so it means that there exist V1, V2 belonging to V such that F of V1 is equal to W1 and F of V2 is equal to W2. So because once again, the whole vector space W from here is generated from the vector space V by application of isomorphism to all vectors in V. Okay. So then, what can I get from here? So let me consider linear combination. Oops. Arbitrary linear combination in C1, C2 belonging to the set of real numbers. So, okay, how can I write this? I can write this as using this and that. I can write this as C1 F of V1 2 F of V2. Okay, wonderful. But now, using the fact that F preserves structure, pay attention. The fact that that F preserves structure, I can use because we start from the statement that F is isomorphism, right? And now we are proving that the inverse of F is also isomorphism. So because I know that F preserves structure, so this statement I can write as F C1 V1 C2 V2, right? Like that. But then inverse function applied to the original function gives me this. From the other point of view, so from here I can write that V1 is inverse of W1, right? And from here, I can write that V2 is F inverse applied to W2, right? So you see, I started from here and I got this statement. So it means that my F inverse preserves structure, right? Clear or not? Because we have proven before exactly this lemma, which says that from here follows this, right? Which is exactly preservation of structure. Is it clear or not?
Yes, it makes sense.
So you see, essentially, when you're given, when I ask you to show that something is isomorphism, first you need to show that between two vector spaces, that first you need to show that for every result, so for every vector in the resulting vector space, like here, you can find, so this one-to-one and on-to, you can find the vector in this vector space, and this vector is unique. And then also you need to check preservation of structures, right? Structure. So, okay, now I can formulate very, very important statement. And this is why it's theorem. Isomorphism is an equivalence relation between vector spaces. Between so essentially, okay, what we need to prove that this relation is symmetric, reflexive, and transitive. So reflexive means that any space is isomorphic to itself, first of all. This is so any vector space is isomorphic to itself. So we just all we need to do, we need to show that identity is identity map is isomorphism. Okay, so I leave it as an exercise because it's easy. So to show that identity map which doesn't change the vector is isomorphism. It's clearly one-to-one and onto, right? So and then all you need to do is to prove preservation of structure, which is extremely simple. So it's reflexivity. So now symmetry. Symmetry, in other words, if V is isomorphic to W, then W is isomorphic to V. So lemma before. Okay, now all we need to do, we need to prove transitivity. I will explain what it is now. So it means essentially that if F, which maps V into W, is isomorphism, and G, which maps W to U is isomorphism, then G, the combination of G and F, so usually we write just a small thing like that, which will be map from V to U, is also isomorphism. So essentially, one-to-one and onto, essentially correspondence over correspondence is a correspondence, right? So that's easy. So if we have, if every vector in here can be obtained as application of F to some vector in here, right? And then we apply another isomorphism like that, then clearly we have correspondence like that. So the only thing is we need to prove that this composite function G applied to the result of F, right, is also preserved structure. So, and this is relatively easy. So we start from C1, C2 real numbers, and V1, V2 belong to the original vector space V. So start from here. Then by definition, what does it mean? It means that we apply G to the result of application of F. Like that. But then following the fact that F is isomorphism, it preserves structure. So I can write that this is nothing else but that. And then I can, following the fact that it preserves structure as well, I can write that this is this. But then it's nothing else but exactly this composite function. So I have shown that this composite function preserves structure. So I have shown transitivity. This is the end of the proof.